So in other tutorials I've described how to create a line and multi-segment features using either Cartesian lines, polar lines, or features such as polygon, rectangle, circle, arc. The final two ways to generate lines or multi-segment features really are with line equation and line equation polar. So with line equation, this is going to be in Cartesian coordinates. And what we have is a formula for the x, y and z values of this line. T start and T end. So this is a way that mathematical lines are often defined, where you give an equation for x, y and z in terms of t, and then you choose what values of t. So if you wanted a line which was y equals x, and it would just be a straight line through the origin, then you can say y equals t, you can say x equals t, and now you can choose where you want your line to start and end. So if you say t goes from 0 to 10, that means the x formula will go from 0 to 10, and the y formula will go from 0 to 10, so you would get a line that goes from the origin to the point 10, 10. So that's how that works, which I'll show shortly. And then we need to choose the number of segments, and the rest is all kind of similar to how it is defined for a line, but these can also be equations instead of just values. So for the x formula, y formula, I'll give that example I just said. The way that you actually define values in these formulas is listed in these cells. So for x and y equations, you can use t val or z val, so they can be a function of z. For the z equation, it can be a function of t, x, y, or the current z. And then for the other equations, which are going to be the width, height, extrusion override value, or speed, we need to use the t start, x start, y start, or z start, or similar for the end or the mid. So the reason that these are using val, the x, y, z equations are using val, and the others are using either start, mid, or end, I will explain that in a bit. But you need to just remember that you have to use t val or t mid, end, or start for these ones respectively. And then the order of which FullControl calculates things. So these are not done iteratively. So if you've got an equation where one is dependent on the other, then you'll need to bear in mind that calculation order. So for the x formula, I said as an example, we can do x equals t. So that means I have to write t val. And the y formula I'm going to do is exactly the same. Z formula is going to be 0. And now my x and y are going to go from this value to this value. So I'm going to go from 0 to 10. And I put the line equation feature down here as well for reference. And then I'm going to do it in 5 segments with the nominal width of 0.5, nominal height 0.2. I'm not going to have an equation for the E override, so I'll delete that. I'm not going to have an equation for F speed, so I delete that. And the tool I'm just going to delete and leave it as the default tool. Separate tutorial we discuss how to change tools. So if I generate the G code for this, it should print a line going from t being 0 to t being 10, which means x should go from 0 to 10, y should go from 0 to 10, z should always be 0, and there should be 5 segments in it. So there's my line going from 0 to 10 in x and y, and it's got 5 segments. So now in my formula, if I want it to go from 50 to 60, then I can do my equation as 50 plus t val for x and 50 plus t val for y. So now they're going to go from 50 plus 0 to 50 plus 10 because t is going from 0 to 10, and that's our equation up there. Our lines are generated. So now if I wanted it to go twice as far, I could either change the t val to go from 0 to 20, Or I could actually change the equation here. So if I return the t-val to go from 0 to 10, and let's say 50 plus t-val times by 5, and 50 plus t-val times by 5, that means it's going to go from 50 to 0 times by 5, which would just be 50, to 50 plus 10 times by 5, which would be 100. So this should give a line that's going from 0 to 100, even though t-val is only going from 0 to 10. And actually, generally I try to use t-val just going from 0 to 1, and then I do all of the other bits in here. So to get an equation that goes from 50 to 80, then I'd do 50 plus t-val times by 30, and I know t-val is going to go from 0 to 1, so I know this term on this bit of the equation on the right hand side is going to go from 0 to 30. So that should give me an equation from 50 to 80, and that's a nicer way of thinking about it, because let's say we don't want to move in exactly the same amount in x and y, we want to move twice as far in y, then we can just change this equation to be t-val times 60 instead of 30, and we've got our equation, but we haven't changed t-val. So t-val is a nice neat number, and that makes a bit more sense. And this equation is still giving out 5 segments. So if we make it a little more complicated, and we do t-val to the power of 2. So now we're going to square t-val, which is going from 0 to 1. So if you square 0.5, you get a value of 0.25. So now it won't be a linear line anymore. It's this curve shape, and you can see it's quite segmented at the bottom. So I might change my number of segments to be 100 instead of 5. And it's now much smoother. And we can see how long each segment is by coming down each line of G-code and Reproduction host. So then we're free to change it however we want. We could do it to the power of 5, and then we get a much more slow increase in the y value. This. We could use a sine wave. Anything that Excel can understand, you can write in here. So I could actually put a formula containing an if function. So if I said if t-val is bigger than 0.5, then I want, and I know how Excel works, but if you're not sure, then just there's lots of guides online about how to use formulas in Excel. But yeah, if t-value is bigger than 0.5, then I'm going to set my y value to be 50. Otherwise, if t-value is less than 0.5, then it's going to be this equation. And actually, if you put an equals at the beginning, then it's quite good to check that all your brackets match up, because Excel, although it won't be able to figure out what this equation means, you do need to get it in the right format. So I need a bracket on the end here to close that, and just tell you this is my logical test for the if function, this is the value if that function is true, and this is the value if it's false. So basically, for the first bit of the line, when t-value is less than 0.5, it will just be doing this equation that we previously were. But for the second half of the line, it's now going to shift and only give a value of 50. And that's what you can see there. Obviously, if I didn't have it at such a high power, then it would be easier to see. And this is a printed line because the beginning of this line was fitted with the Excel if formula, and the end of it didn't. So it is a printed line, and its width is going to be calculated according to width and height, just like all the rest. So we'll see one line will have a much bigger extrusion than all the rest, So these ones all have values of E 0.05, 0.06, and then this one has a value of 1.5 because it's printing a really long line, and then all the rest have tiny extrusion values. If we wanted every line to have exactly the same value of extrusion, then we can use this E override formula and just say we want it to be 0.05 for every line. And now you can see the E value has been set to 0.05 for every line. We could also have the E value as a formula, which I'll discuss shortly. So that's how we define a formula. Most of the time you're not going to use an if function. Sine waves are a great formula to use. So typically I do a sine wave as saying, let's say x is just going to increase linearly with t, and we're going to go from a value of 50 to a value of t times by 50, which means because t is going to go to 1, we'll go from 50 to 100. And then for y, if we do sine, and t-val is going to go from 0 to 1. So if we do sine of t-val, that formula will work, but it won't give us a full sine wave, because the sine wave should go from 0 to 2 pi. So if I times t-val by 2 and then use the XL function for pi, this will now do a full sine wave as t goes from 0 to 1. So if I generate the G-code for that, you can see it's put the sine wave down there, and it's got an amplitude of 1 because that's what a sine wave has. So if I firstly multiply it by 10, this means it will have an amplitude of 10. And secondly, I probably don't want it at a value of 0, so I can say equals 50 plus all that stuff on the right. Now it would all oscillate around a y value of 50, so it will be up here. And then with the sine wave, if you want to double the frequency, then within the sine, you can just multiply it. So if I do 5 times by all the other stuff, then it will be a frequency 5 times what it currently is, or the period will be a fifth, so we get 5 sine waves as t goes from 0 to 1. And this is why I tend to keep t value 0 to 1, because you can play around with the formulas to get what you want without having to balance how the x value or the x formula for t-val and the y value for t-val are kind of interacting. So that's sort of an introduction to doing the x and y, and then the z formula. At the moment I've just put 0. It's very easy to do a kind of spiral, like bars mode printing. If you just say for each layer, z-val is going to go from 0 plus t-val, and then times by whatever the height of your filament is. So I'll put t-val times by 0.2 here. And what that means is our z value will gradually increase from 0 to 0.2, which we can see z value is going to, it's going to 0.4 from a value of 0.2 because I'm offsetting the whole toolpath by 0.2 here. So when I design starting at 0, it's all offset from the print bed by this initial value to give the nozzle space on that very first layer. So that's our equation. So I'll put the x-val. Just sort of one more interesting thing. We might want, let's say we wanted to do a toolpath where the tips were higher than the middle. Then we could use exactly the same kind of sine wave to go up then down and up and down as we've got for the y formula. So if we did 10 times by sine, this won't quite work because it's going to have negative values, but it will show you kind of what I mean. So you can see that as z value is now changing. Obviously we wouldn't be able to print this, but it just shows you. And if we didn't want to go to negative, then we could use, as I say, any XL formula. So if I put in absolute, now it's going to make sure they're all positive. And if I only wanted it to increase by 1 instead of 10, then I can just change this. And now it'll be printing at a more shallow angle. So we have our control over X, Y, and Z formulas. So I'm going to return the X formula to be just 0. Now for our other equations. With our X, Y, and Z formula, basically it's splitting a long line up into 100 segments. And for each segment, it's kind of finding the end point of that segment. And it knows what the end point is because it's dividing t 100 times. For width, height, extrusion, and speed, they're slightly different because they're set for a whole segment rather than the end of a segment. So whereas here the line is, we're defining the coordinates in terms of the beginning and end of segments. Here it's for the whole segment overall. So we need to say, if we're making these formulas a function of X, Y, or Z, we need to say, for this segment, do we mean the beginning of the segment, the end segment of the segment, or the middle of the segment? So then if I do one for extrusion override, well, let's do it for nominal width. Currently we can see we've got an extrusion value of 0.05. That's because we've done an extrusion override. Fine. So then if I do that as a formula of 0.05 plus t-val times by 0.05, that means the extrusion is going to gradually increase from 0.05 to 0.1. And I've made that mistake. It can't be t-val. It's got to be t-mid, t-start, or t-end. So if I do t-mid, that means the middle point of this segment is going to be used to calculate what the value of the extrusion should be. So we can see that it starts with 0.05, just above, because it's the middle of this segment, not the very beginning of it. And then it gradually increases to 0.1. It's again just below, because we're not using the end of the segment, we're using the beginning. If I had used the end, so t mid, if I change that to be t end, it would now reach properly 0.1, as we see here. But would be slightly worse at the beginning, or it'd be slightly further away from 0.1. So the mid value is typically what you'd be going for. If I get rid of extrusion override, in actual fact for this structure, because the lines are of different lengths, the segments, this segment is quite long and then this one is quite small, long, 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 small, small, small. That's because the X equation is linearly split. So the long segments have a higher extrusion amount than the short segments. And that's because FullControl is pumping out the correct amount of material to achieve this width and height. So I wouldn't use E override unless all your segments are of the same length. Really, if you know what you're doing, use E override, otherwise just change width. So if I used 0.5 plus t-val times by 0.5, that means our width is going to vary from 0.5 at the beginning to 1 at the end. Again, can't use t-val for these ones, have to use t-mid. Then you'll see at the end we're getting extrusion rates varying from about 0.13 to 0.6, and at the beginning it's going from about 0.3 to 0.07, so it's about half of the extrusion that is at the end. So this would print gradually wider and wider and wider, so it would end with a double width, then it begins. And you can do the same with the speed. You could have speed gradually increase, or again we could use our sinusoid function for speed. So for speed, this value is actually a parameter called nozzle feed rate printing. So if I do speed is going to be equals nozzle feed rate printing as a parameter and then times by our kind of the absolute of this sine wave. Again, I have to use T mid. Then what we'll find is speed is going to vary at f speed, and you can see speed as the colour map here, where in the middle it's at a value of 80, and then it's increasing up to almost 1000 and then back down to 80, and that's, you know, we could inverse this so it would print the top bits slower instead of faster. We could have it so it's printing the top bits thicker or thinner than the middle bits. You can put lots of different interesting quirks into speed and extrusion rate when you start printing mathematical formulas. Okay, I think that's most of the important things for line equations. Polar equations are very similar. I'll do a separate tutorial for them, and also if you do a repeat rule with a offset linear maths or offset polar maths, then that's going to be an x offset, y offset, z offset as a mathematical equation. Again, so we have to use the same terminology as we used for the equation to define a line. So you could do a repeat rule with the mathematical offset applied to a non-mathematically defined line. I'll describe that in a separate tutorial though. And the final one is post-processing, but that again will be a separate tutorial. Okay, repeat and reproduce and recalculate is also quite an important one, just to mention briefly. So instead of, if you do Cartesian repeat of this structure, then it's not going to recalculate the equation every time. It's just going to look at the print path that was generated for feature 1 and then repeat it with whatever offset we choose. So if we did a 0.2 offset in the Z, it would just repeat all of the lines for feature 1 up in the Z exactly as they were. However, if we wanted something to change as we were moving up a structure, we'd have to use reproduce and recalculate. I'll do a separate tutorial for that, but just very quickly to show what I mean. If we have our y formula is a function of z-val, I'm just thinking, I don't think y can be a function of z. Yes, it can. So if y is a function of z-val, then what we could do is have the amplitude of our sine wave, which is this 10, multiplied by, let's say z-val, just for simplicity. So initially it's going to be 0, and then it's going to get higher and higher and higher as we increase and go up through the through z. And I'll just get rid of that 10 times. So it's just going to be z-val times by a sine wave, which has an amplitude of 1. So now if I generate that equation, it should just be a straight line. And there we go. We've still got our speed things. I can delete that now, I guess. So we've got a straight line because z-val is 0, so our y equation is coming out as just 50 times by 0. Now if I do Cartesian repeat of this, it would just do a straight line up as many times as we want. So if I do that, if I do a Cartesian repeat of feature 1 with x, y displacements of 0 and then 0.2 in z, and if I do 50 repeats of that, 49 to get a nice neat number, and that will give me a 20mm high structure, which looks like this, because it just repeated the line all the way up. But now if I skip this one and do the reproduce and recalculate feature. So now I'm going to reproduce and recalculate feature 1. I'm going to do it 49 times, and it's not going to change in X and Y, it is going to change in Z 1.2, and then I need to delete these other bits, which I'll discuss more in the other tutorial that discusses this. But now it's going to recalculate them, so it takes longer because it's doing the mathematical equation calculations every single time, but each time it's now using the current value of Z. So you see the sine wave is gradually increasing as we go up in Z, because the equation has been recalculated with a new value of Z each time. So there'll be a new tutorial later showing reproduce and recalculate in a bit more detail, but that's basically the big difference between reproduce and recalculate or simply Cartesian repeat.